In the first video, we learned that in fact the energy level and sublevels were related. Namely, there were as many possible sublevels of energy as whichever level it was you were looking at. However, we also learned that a great many of these sublevels are never used and never seen because you would need atoms so large with upwards of a couple of hundred electrons that we have no need for these further sublevels. Once you get past the fourth level with its four sublevels, we see only four max in the fifth level. Now, what's all this got to do with anything? Well, if we go ahead and check out the periodic table, is the table's arrangement coincidence? Well, for the purposes of our discussion, picture helium as living right here above group 2. Now, of course, hydrogen is not really a metal, and it's not one of the alkali metals, but it does behave like them chemically in many ways, so it's in group 1. Now, helium behaves chemically like the noble gases and belongs in group 8, but for the purposes of our discussion, it's easier if you envision it as existing right here. Now, if you do so, you see that this fraction of the periodic table is 2 atoms wide. Now, we learned earlier that, in fact, there are 7 possible energy levels. And if we look at the periodic table, it's no coincidence that there are 1, 2, 3, 4, 5, 6, 7 periods from 1 through 7. Now, we also know that in the first energy level, there is room for only one sublevel, the S sublevel. And since an S sublevel can only contain 2 electrons, it's not surprising that this is 2 atoms wide, this section of the periodic table. Now, don't forget, every single energy level, or I should say every principal energy level, has an S sublevel. So then again, I'm not surprised to see that all 7 periods have this section of the periodic table that's 2 atoms wide. And we're going to call this the S block of the periodic table. Now, once we get to at least the second energy level, n equals 2, we start seeing the presence of p sublevels. And of course, every energy level after this second energy level, and including it, should have a p sublevel. So again, it's interesting to note that if you look in the first period, there's nothing over here, only right here in the S block. But once you get to the second period, you see that you have this block included as well. And not coincidentally, it's 1, 2, 3, 4, 5, 6 atoms wide. And don't forget that a p sublevel has 3 orbitals and can accommodate 6 electrons in those 3 orbitals. So, is it a coincidence that this is 6 electrons wide? No, it's not. This is called the p subblock of the periodic table. And there is no 1p because in the first principal energy level, there's only one sublevel, and it's S. It's not until you get to the second energy level, principal level, that you see 2 sublevels, S and P. Now, let's not forget that if a D sublevel exists, as it would beginning with the third energy level, then that D sublevel would have 5 orbitals and could accommodate 10 electrons. Well, if you look at this chunk of the periodic table right here, you'll notice that it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms wide. And yes, in fact, this is the D subblock. And you may be asking yourself, well, why? If in the third energy level you have an S and a P and should have a D, why is this blank right here? And I'll get to that momentarily. That has to do with the relative energies of the sublevels. But lastly, beginning with the fourth energy level, or n equals 4, you can have an F sublevel. And if you remember from our orbitals, an F sublevel has 7 possible spaces in which to put electrons. And in 7 possible orbitals, you could accommodate up to 14 electrons. Now down here, below the periodic table, though it really exists between the S and the D block, you see a stretch that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms wide. And yes, this is the F block. And no coincidence, yes, it's 14 atoms wide. Now, you really need to picture the periodic table this way. And it's really what I was just showing you right here. Namely, this stretch over on the left side that's 2 atoms wide represents electrons in the 1s, 2s, 3s, 4s, 6s, or 5s, 6s, and 7s sublevels. And that this P block begins with 2p, because the first principal energy level that can have a P sublevel is the second one. So this is 2p, 3p, 4p, 5p, and 6p. Now this middle section of the periodic table for the transition metals is called the D block. And let's not forget that to have this third type of sublevel, you have to be at least n equals 3 for a principal energy level. So the very first one I see is going to be the 3D, then the 4D, then the 5D, and if we needed it, 6D. And then lastly, the stretch that fits here between the 6S and 5D and starts right here. If you want to look at the periodic table itself, it looks more like this. 57 comes after 56, 56, 57. So yes, the F block fits between the S and the D right there. And so yeah, the first time you would see an F sublevel, because that's the fourth type of sublevel of energy, is when n equals 4. So yes, it's not till the fourth principal energy level that you see an F sublevel, and this is 4F, and the one higher than that is 5F. Now, this is kind of interesting, because this tells you the increasing sequence of energies. Yes, 1s comes first. It's the lowest possible energy. Then comes 2s, the next highest energy. But after 2s comes 2p, and that makes sense because 2p electrons have more energy than 2s electrons. Once you fill the 2p, you begin to put electrons out in the 3s sublevel, because 3s has more energy than a 2s or a 2p. And after you fill your 3s, you begin to fill your 3p sublevel with electrons. Then after 3p, you begin to fill the 4s. But interestingly enough, even though this is the fourth period, the first group of D electrons is the 3D group. Let's not forget, to have a D sublevel, you have to be n equals 3 as a primary energy level. So after 4s comes the 3D. Now what this is saying is, yes, an electron in a lower principal energy level, 3, versus a higher principal energy level, 4, can in fact have more energy if the electron's in a 3D and the other is in a 4s, because 3D comes after 4s. So this is counterintuitive. You don't expect an electron in a higher principal or a lower principal energy level to have more energy than a higher principal energy level, but in fact that's what the periodic table is telling me. 3D has more energy than 4s. Then 4p does have more energy than 3D. Then 5s, and then after that we see the same thing, that 4D, lower principal energy level, has more energy than 5s. And then 5p, and then 6s, and here's the real kicker. After 6s comes 4f. That's right, a 6s electron has less energy than a 4f. And you may be saying, how would I ever remember that? Well, if you have a periodic table, you can remember that. Because if you count 51, 52, 53, and I'm wondering, okay, what block am I talking about? Well, this is the P block. P block begins with the second energy level, so this is 2P, this is 3P, this is 4P. I'm counting 5 P's here. When I get to 54, after 54 comes 55. And this is the S block. And of course, it's the 1, 2, 3, 4, 5, 6S. So yes, after 5P comes 6S. But after 56 comes 57. Oh my goodness. And this is the very first F, which is, of course, the 4F sublevel. So looking at my periodic table, since 57 follows 56, it makes sense that 4F has more energy than 6S. This is referred to as Aufbau principle. It's a fancy German word for building outward. We are, in fact, placing electrons in higher and higher sublevels based upon their energy. And the periodic table is arranged to reflect Aufbau, namely 4F electrons are placed after 6S electrons because 4F electrons have more energy than 6S electrons. In other words, I can think of the periodic table this way. 1s, 2s, 3, 4, then 5 is 2p, then 11, 12 is 3s, then 13 through 18 is 3p, 4s, then 3d, and then 4p, and then 5s, and then 4d, 5p, 6s, but then down here to the lanthanides, 4f, and then 5d, 6p, 7s, 5f, and lastly 6d and 7p. So yeah, it's very helpful to have a periodic table to remember it. Or you could draw this cute little diagram. Namely, list by energy level what sublevels you have. Here we list the fact that we have a 1s, and in the second level 2s and 2p. In the third level 3s, 3p, 3d. Next level 4s, 4p, 4d, 4f, etc., etc., etc. And then just draw arrows diagonally backwards. 1s, 2s, 2p, 3s, so 2p less energy than 3s, 3p, 4s, and then after 4s, don't forget, after 4s comes 3d. So I can see that. After I fill 4s, I go back to 3d, so 3d is higher energy, then 4p, then 5s. And then after 5s, look at your periodic table, after 5s comes 4d. Well, that means after 5s on this diagram, I should go to 4d, then 5p, then 6s. And after you fill the 6s, then you fill the 4f. Again, look at the periodic table. After 6s, 56, comes 57, 4f. And then 5d, 6p, 7s. And then 5f, 6d, 7p. So yes, the highest energy electrons in any configuration are in the 7p sublevel. Yep, the 7p sublevel right down there. Highest energy electrons. And we can also visualize the sequence this way in terms of actual energies. Yes, the 1s has less energy than 2s, 2p higher than 3s, then 3p, but 4s has higher energy than 3p, and 3d has more energy than 4s. Then comes 4p. Then comes 5s, 4d, and then 5p, 6s, 5d, 4f, then 6p, 7s, 6d, 5f. And if it were on here, after the 5f would come the 7p. Well, actually, 6d then.